Tonight we're starting our last kind of big thing in AP Chemistry. We're just getting into electrochemistry. We're just going to start off with a little bit of review from first semester, and it's simply going to be redox reactions. And redox reactions always involve the transfer of electrons. Transfer of electrons. Just like acid-base reactions pretty much always involve the transfer of hydrogen ions or protons. Then our first thing is simply going to be we can have oxidation happening, or we can have reduction happening. And oxidation is Leo says Gur, so it's the Leo part, so it is the loss of electrons. And then the opposite of that is reduction, and reduction is the Gur part of Leo says Gur, and it is the gain of electrons. Alright, and a couple of examples of this might be if we have copper metal. Copper metal tends to lose electrons, so we might have something like this, and this would be known as a half reaction. Alright, or I guess conversely, we could have zinc plus 2 electrons, so it is gaining electrons, turns into zinc metal. Alright, so we start with a zinc ion, we add a couple electrons to it, and we get zinc metal. Alright, the next part is really kind of the meat of electrochemistry, and if you can understand this, you're pretty much good for electrochemistry. And it is going to be what's known as a galvanic, or a voltaic cell. And this is pretty much a battery. And essentially galvanic or voltaic cells always generate electricity. Through the use I'm going to abbreviate that, through the use of spontaneous chemical reactions. And the key word here is spontaneous. So we're just going to highlight this. Spontaneous. And spontaneous refers explicitly to galvanic or voltaic cells. Alright? So if you can have spontaneous with galvanic, we're good. And let's see. We're just going to say the structure, or their structure. Nothing happens. No, I think we're just going to draw a picture. So here we go. We're going to jump right into it. So a galvanic cell looks something kind of like this, where we're going to have some beaker. It's going to be on the left-hand side. We're going to have another beaker on the right-hand side. Alright, and in my left-hand beaker, I am going to have a piece of zinc metal. So we can call this zinc. And in my right-hand beaker, I am going to have a piece of copper metal. Copper. And let's see, in my jar on the left, I got some liquid in here. And this liquid is, let's just say it has zinc nitrate in it. Zinc nitrate. So we really have some zinc ions floating around and some nitrate ions floating around. Alright. In my copper one, we can just say the same thing is happening in my copper. So we've got some liquid, and let's just have its copper nitrate. Oops. So we're going to have some copper ions floating around and some nitrate ions floating around. Alright, we can get rid of that plus. Alright, so we have a couple solutions. Alright, it doesn't much look like a battery, but we're going to make it a battery here very quickly. So what we can do is we can just hook a wire to the top of our zinc. And this can go this way. We're going to have another wire that hooks to our copper. And between these, we're just going to put a voltmeter. Voltmeter. And this will tell us how many volts are being conducted across our cell. Alright, so we have our voltmeter, and if we were to look at a table of standard reduction potentials, which is available to you on the AP test, so this is just going to be called standard reduction potentials. Reduction potentials. It is going to look something like this. Something kind of like that. It's going to be a big list of ions and some voltages over on the right hand side. We're going to find, if we compare copper and zinc, that copper is way up here kind of towards the top, and zinc is kind of way down here towards the bottom. And all that says is copper is more likely to be reduced than zinc is to be reduced. Alright? So what that says is copper, if we look at it, if we're comparing copper and zinc, copper is more likely to be reduced. So really copper is more likely to gain electrons, alright, and turn into copper ion than zinc is. Alright, in any kind of cell, only one thing can be reduced and one thing's going to be oxidized. So if copper is being reduced, it means that zinc necessarily is going to be oxidized. So our half cell for zinc is going to look something kind of like this. Yeah, alright. So what that means is our zinc piece of metal, this reaction that we've just written, is going to happen on this side of our kind of cell. Alright? So zinc metal is going to be turning into zinc ions. Alright? What's going to happen to these electrons? Well, those electrons are going to flow this way around our wire. They're going to thread through our voltmeter. And then on the other side of our voltmeter, they are going to go through our copper, piece of copper. And do we have copper ions floating anywhere? Yes, we do. I messed up right over here. This should be copper 2+, plus 2 electrons makes copper solid. So these copper ions are going to combine with the electrons that are flowing to make more copper metal. Over here, our zinc metal is going to turn into zinc ions. So essentially, we're going to have a flow of electrons flowing from our zinc to our copper, alright? Because copper is more likely to be reduced and zinc is more likely to be oxidized. However, this will only happen for about a split second. And what happens is we have a charge imbalance. Alright? So our zinc side, we are dumping positive stuff into our liquid, and positive is building up over here. So positive is getting quite large. Over on our copper side, because copper ions are being removed from our solution and nitrates being left, we have a big buildup of negative charge. Alright? And this is bad. It's going to impede our flow of electrons. So, in order to make this work, we have to have what's called a salt bridge. Alright? And a salt bridge is just anything that has small electrolytes in it. So I'm going to draw a salt bridge. And it is going to be kind of right here. Something kind of like this. Alright, it's going to connect our two things. And it might have something in it such as, we could do potassium chloride in this particular one. Alright? And because our left side is building up positive charge, we're going to have chloride ions flowing towards this side. And on the other side, because it's a buildup of negative ions, we're going to have potassium ions flowing this direction. Alright? So a couple things about our cell. The side that's being oxidized, so in this case is our zinc side, is known as the anode. Alright, and the easy way to think about that, anode, oxidized, they both start with vowels. Whatever's being oxidized is the anode. Our copper happens to be the cathode. Alright, and what happens at the cathode? Our thing is being reduced. So they are both consonants. So reduction happens at the cathode, oxidation happens at the anode. And then electrons always flow from anode to cathode. And that, if you just think alphabetically, A comes before C, so electrons are going to flow from A to C. Alright, so that is a galvanic cell. The next thing we're going to look at is basically what's called cell notation, or line notation. And we're just going to have letter B, and this is line or cell notation. And for line or cell notation, we're going to define a couple things. Two straight lines are going to represent or equal the salt bridge. A single line is going to represent a phase boundary. So this would be, in our current example, it would be between our aqueous and our solid. Okay, so we have a piece of zinc metal and we have zinc ions. So our zinc ions are aqueous, our zinc metal is solid. And that is really it. Alright? So a line notation is going to always, again, be something like this. We are going to write this. The first thing, just from left to right, is going to be the anode terminal. Then we're going to have a phase boundary, and next to the phase boundary is going to be the anode electrolyte. And then we're going to have a salt bridge, and then we're going to have the cathode electrolyte, and then a phase boundary to the cathode terminal. So our cell above, what we would write is our anode is zinc. So write as zinc. And we're going to have a phase boundary, and it's going to Zn2+. And then we're going to have a salt bridge that really connects our zinc 2+ to our copper 2+. And then our copper 2+ is separated with a phase boundary by our cathode terminal. Alright? And this is just a shorthand way to write our big galvanic cell that we have written above. Alright? So our next thing is going to be C, which is electrical work. Alright, electrical work. And really, electrical work is concerned with how much work can be done, how much, and how is it measured. Is it measured? Alright, so the first thing is, it is measured by a unit called electromotive force. Alright. So we're going to say electromotive, not locomotive, but electromotive. Ooh, electromotive force. And we're just going to abbreviate this every time EMF. Alright? And EMF is based on standard reduction potentials. Alright? Which is how I found out what our cathode and anode were. Based on reduction potentials. Potential. Whoa. Reduction potential. And everything is measured against hydrogen. So as we kind of look at our standard reduction potentials, again, if we take this out, you're going to see that hydrogen is right in the middle, and it has a voltage of 0. So everything is based off of hydrogen being 0. And because it's standard reduction potentials, standard conditions, kind of like we have standard potentials for just about everything, but standard conditions are always going to be a temperature of 25 degrees Celsius. Our concentrations are always going to be 1 molar. And our pressure is always going to be 1 atmosphere. Alright, and if that's true, hydrogen is 0. If it has a positive, or we'll just write this here, hydrogen, and this half reaction looks like this, 2 H pluses plus 2 electrons yield hydrogen ions. Okay. And again, notice this is written as a reduction because we're gaining electrons. So it's written like this. It has an E value of 0 volts. And if something is a positive E, alright, so hydrogen is 0, something has a positive E, all that means is it's more likely to be reduced. More likely to be reduced. Which means as well it is a stronger oxidizing agent, because things that are more likely to be reduced are oxidizing, more strongly oxidizing agents. So strong oxidizing agent. I know I wrote strongly, but it's there. Alright? If something has a negative E, it is less likely to be reduced. If it's less likely to be reduced, it is a weak oxidizing agent. Weak oxidizing agent. I already put a Q there again. If it's a weak oxidizing agent, it's a strong reducing agent. Conversely, a strong oxidizing agent is a weak reducing agent. Alright? So that was essentially electromotive forces number 1. We're going to have another couple things to talk about. Alright? Number 2 is going to be standard cell potentials. So standard cell potentials, it is always the case that E cell is always going to have a value that is equal to E of the reduction minus E, this is an equal sign, E of the oxidation. Alright? So if we look back up at our galvanic cell, up here, we had, and we're looking for reduction minus oxidation. Who was reduced? Copper was reduced, and zinc was oxidized. So if we go back to the bottom, where we were just at, alright, and we look up values and a standard reduction potential guide, we're going to see that copper plus 2 electrons, which is what happened, that was our reduction reaction, has an E value of 0.34, oops, I did 0.34, or 3.4, has a value of 0.34 volts. This is positive. Conversely, if we look at zinc, alright, zinc plus 2 electrons going to zinc, alright, notice it's always written as a reduction. It has an E value of negative 0.76 volts. So E cell is always reduction minus oxidation. So it is simply 0.34 volts minus negative 0.76 volts, or 1.0 volts. Alright? And that is simply what you do. These values that we have over here on the right are right off the table. Alright? Some of you are going to ask this, so I'll just put it out there. It might confuse others of you. Notice that this equation is written backwards. Alright? So if we switch this equation, this really becomes a positive 0.76. So if you think of it in terms of that, we're really adding our potentials. We're adding reduction plus oxidation. But if we look at just our straight numbers, we're always taking reduction minus oxidation of what the numbers are on the table. Okay? The last thing we're going to do is just have another example. And our next example is a little bit different. So it is a good and important example. But it is going to be find the E cell. Find E cell and the balanced equation. And balanced equation for the following. Alright, so we're going to have aluminum ion plus magnesium is going to yield aluminum metal plus magnesium ion. Okay? So from that, a couple things are true. If we look at our half reactions, we can see that we can write the half reaction for aluminum as this. Aluminum plus 3 is going to, what is it going to be? We're going to add that to 3 electrons. Plus 3 electrons is going to yield aluminum. And then our other reaction is going to be magnesium is going to yield Mg2 plus 2 electrons. So aluminum is going from a plus 3 oxidation to a 0 oxidation, so it is being reduced. Alright? Magnesium going from 0 oxidation to a plus 2 oxidation, so it is being oxidized. So this is our anode. And up here is going to be our cathode. So cath and anode. And cathode. Alright, so kind of once we write these, we can go ahead and balance this equation. Alright, because we're going to balance our electrons. So we really need to multiply our reduction half reaction by 2 to get 6 electrons. And we're going to multiply our oxidation half reaction by 3. So we really want 2 aluminum plus 3s. Plus 3 magnesiums is going to yield 2 aluminum metals plus 3 magnesium ions. Alright, we have 2 aluminums on both sides, we have 3 magnesiums on both sides, we have a plus 6 charge on the left, we have a plus 6 charge on the right. Alright, so that is completely balanced. Now, to get the second part of our question was, what is the E cell? Alright, and E cell, again, is reduction equals reduction minus oxidation. Alright, so we need to look up tables in our chart. And we're going to find that the reduction for aluminum is negative 1.66. Decimal in the wrong place. It is negative 1.66 volts. And for magnesium is negative 2.37 volts. So if we set up our equation, we're going to have negative 1.66 volts minus a negative 2.37 volts. Or we're really going to be adding, or subtracting a negative, so we're really adding that. And we get a value of 0.71 volts. Alright? And that is our answer. So what is interesting about this is, what does voltage not depend on? Alright? What does voltage not depend on? And this is super important. E cell, or voltage, does not depend on how we balance our half reactions. Okay? So it does not change. Voltage does not change. Does not change. Does not change. If we multiply our half reactions. So even though we had to multiply our reduction reaction by 2 and our oxidation reaction by 3, notice that is not translated into our E cell. Alright? And that is it for 14.1. It was kind of a long one. Super important stuff. If you understand the galvanic cell right up here, this is key to understanding electrochem. Alright? Have a great night.